Welcome! In this video we're going to solve some Bernoulli equations and then we're going to do some applied examples. So you'll have a look there on the left. I have the problem set that I'm going to do. I'm going to write it here on the right hand side. So let's begin. So what is a Bernoulli equation? It's an equation of the form y dash plus p of x y is equal to q of x y to the power of n, where n is a real number. N is an element of the set of real numbers, that says. Okay, so how do we solve this? Well, we set out by letting z be equal to y to the power of 1 minus n. And then what we do is differentiate this with respect to x. So z dash is a function of x. Now to differentiate this, we need the chain rule for differentiation. But what that does is it brings down the 1 minus n, subtracts 1 from the exponent. So 1 minus n minus 1 is minus n. And then we have to multiply via the chain rule by the derivative of y with respect to x. So y dash of x. Okay, so we have this. And now we want to rearrange this so that we can substitute y dash into our expression up here. So let's go ahead and do that by dividing by this. So we have y dash equals 1 over 1 minus n y to the power of n times z dash. Okay, and so now we can substitute that in there, and so then we get 1 over 1 minus n y to the power of n z dash plus p of x times y is equal to q of x y to the power of n. Okay, and now so we want to express this as a differential equation in terms of z with only z's and x's, and so we expect that we can cancel the y to the n. Okay, so let's go ahead and bring that y to the n over to the other side, or divide throughout by y to the power of n. So then at the same time we can multiply by 1 minus n, and so when we do that we get z dash plus p of x y to the power of 1 minus n equals q of x times 1 minus n. Because here when we multiply throughout by y to the power of minus n, we cancel this y to the power of n, and this is what we're left with on the right hand side. Okay, now let's make an observation. Since we let y to the power of 1 minus n be z, this part right here is just z. So we have z dash plus 1 minus n p of x times z is equal to 1 minus n times q of x. And now notice this right here, this coefficient of z is a function of x. And this is also a function of x, since we assume that n is just some fixed real number. Okay, so now this equation is linear. And so what we can do is multiply throughout by the integrating factor. So, in other words, proceed via multiplying by I of x, which is e to the integral of 1 minus n p of x with respect to x. Okay, so this is the approach we take. Now let's try an example. And that'll be our first question, question number 1 on the left. So here we've got y dash plus y is y squared. This is Bernoulli, and here n is equal to 2. So again, we let z be equal to y to the power of 1 minus n, which is y to the power of 1 minus 2, or y to the minus 1. Now let's differentiate z with respect to x using the chain rule. Or actually, let's say that this is a function of t, so we'll differentiate with respect to t. And so we'll get z dash as a function of t is equal to minus y to the power of minus 1 is minus 2, and then multiplied by the derivative of y with respect to t, so we'll call this y dash of t. Okay, and so we want to substitute y dash in that expression in the first differential equation up here. And so now we'll write y dash equals minus y to the power of 2 times z dash. And now we sub this into our equation, and we get minus y squared z dash plus y is y squared. Okay, and so now we want to divide throughout by minus y squared so we can get a linear differential equation to solve. Okay, so let's do that. Dividing by minus y squared, we will get z dash minus 1 over y is equal to minus 1. Now 1 over y is z, so we have the linear differential equation z dash minus z is equal to minus 1. Okay, and so what we need to do next is find an integrating factor. So I of t, our integrating factor, is e to the integral of minus 1 with respect to t, which is e to the power of minus t. And this is what we multiply throughout by. So multiplying by our integrating factor, we have e to the minus t z dash minus e to the minus t times z is equal to minus e to the minus t. Now we know how the left-hand side collapses into a single derivative using the product rule, so let's do that here. So this is the derivative with respect to t of e to the minus t times z. And so when we expand this using the product rule, this is what we get, the line above. So we're using the product rule in reverse. Okay, and now we need to integrate both sides. And so we have e to the minus t times z is equal to the integral of minus e to the minus t with respect to t. This integral is really easy. It's just e to the minus t. And we also need a plus c, a constant of integration. All right, great. So now we're nearly able to solve for y because we can solve for z easily just by multiplying throughout on left and right hand side by e to the power of t. So we'll do that. Z is equal to, now e to the minus t divided by e to the minus t is 1. And then we have plus c e to the power of t. And this is z, but remember z is equal to y to the power of minus 1. So y to the power of minus 1 is equal to 1 plus c e to the t. Okay, now if we invert both sides, we get our general solution that y as a function of t is equal to 1 over 1 plus c e to the power of t. And we've found the general solution to that differential equation. Let's move on to question 2, which is given there. Y dash plus x times y is 6x times the square root of y. Okay, so we need to express this as y to the power of n on there. So let's call this 6x y to the power of 1/2. And so here we see n is equal to 1/2. Okay, so our first step is let z be equal to y to the power of 1 minus n, which is y to the power of 1 minus 1/2, which is y to the power of 1/2, or the square root of y. Okay, and so now we need to differentiate this with respect to x. Z dash as a function of x is equal to, now just looking at it from this point of view, we bring down the 1/2, subtract 1 from that exponent. So 1/2 minus 1 is minus 1/2, and then we need to multiply by the derivative of y with respect to x. Okay, let's simplify this and say, so y dash is equal to 2 y to the power of plus 1/2 times z dash. So this is minus 1/2 in that exponent, and so when I take this over to the other side, the left-hand side, we multiply by 2 y to the plus 1/2, and this is what we get. Okay, so now that we have that, let's substitute this in here. So this is 2 square root of y z dash, right? Because this is 2 root y z dash. And then we have plus x times y is equal to 6x root y. Okay, so now let's divide throughout by 2 root y. And so we get z dash plus xy over 2 root y is equal to 6x root y over 2 root y. Now we need to simplify this. All right, so y divided by root y is root y, but root y is z. So what we have then is z dash plus 1/2 x times z. And then over on the right hand side we have 3x, because the root y and the root y cancel. All right, fantastic. So now we have a linear equation. Our p of x is 1/2 x and our q of x is 3x. So the integrating factor here, I of x is equal to e to the integral of 1/2 x dx. So we have e to the power of x squared on 4. Okay, if you differentiate a quarter x squared, you get 1/2 x. So here is our integrating factor, and we're going to multiply throughout by this. And so we know how the left-hand side packs up. We just have the derivative with respect to x of the integrating factor times z. And then on the right-hand side, we have 3x times the integrating factor, e to the quarter x squared. Okay, now we need to integrate both sides. So integrating both sides, we have e to the 1/4 x squared z is equal to the integral of 3x e to the 1/4 x squared dx. Okay, now this integral should come out via substitution. So we'll say let u be equal to 1/4 x squared. Okay, so when we do this, we know since the derivative is a constant times this 3x, it should work out. So let's differentiate and see exactly how we should substitute, replacing the dx. Okay, so du on dx is equal to 1/2 x. Okay, and so then taking that dx over to the right hand side, pretending like this is a fraction, so we can see what substitution to make. What we have then is we're going to replace dx with du over 1/2 x, but that becomes 2 over x. 2 over x du. Okay, so now our integral is equal to 3x e to the 1/4 x squared, but that's e to the u. And then we're replacing dx with 2 over x du. And so now we can cancel an x. 3 times 2 is 6. We can pull out the 6. So we'll say this is 6 e to the u du. And so that's 6 e to the u plus a constant c. Okay, so e to the u was e to the 1/4 x squared. So this is 6 e to the 1/4 x squared plus c. And so taking this equation and dividing throughout by the integrating factor, we will get z, and remember z is the square root of y, is equal to 6 plus c e to the minus 1/4 x squared. And so if we square both sides, we'll get our general solution. Let's see if I can fit it in here. Y equals the square of this. So 6 plus c e to the minus 1/4 x squared, and then that's all squared. Okay, a bit hard to see, so 6 plus c e to the minus 1/4 x squared, all squared. Okay, and that completes question 2. So let's move on to question 3. Find the general solution to the differential equation y dash plus y equals y to the minus 2 using methods for first order linear ODEs. Okay, so this is a Bernoulli equation. With y equal to, with n equal to that exponent there, minus 2. All right, so given that, what we do here is let z be equal to y to the power of 1 minus n, which is y to the power of 1 minus 2, and that's y to the power of 3. So z is y cubed. Okay, so differentiating this with respect to, say, I suppose we could say that this is a function of x. So z dash as a function of x is 3y squared times y dash using the chain rule. Okay, and so dividing both sides by this, we've got y dash is equal to 1/3 y to the minus 2 times z dash. And so now we want to sub that in. And then multiply throughout by 3y squared. So doing so, we've got z dash plus 3y squared, but y squared times y is y cubed. And so this will be equal to 3 on the right-hand side, because 3y squared times y to the minus 2 is just 3. Okay, now let's have a look at this. Y cubed is z. So we have z dash plus 3z is equal to 3. And this is linear. Okay, and so our integrating factor I of x is e to the integral of 3 with respect to x So that's e to the power of 3x. And so this is what we multiply by throughout. And we know how that left-hand side packs up. It packs up as the derivative of e to the 3x times z, and then on the right-hand side we have multiplied throughout by e to the 3x, and so we have 3e to the 3x. Okay, great. So let's integrate both sides. E to the 3x times z is the integral of 3e to the 3x with respect to x. This integral is super easy. It's just e to the 3x plus c. So to finish this off, we just need to divide throughout by e to the 3x and recognize that z is y cubed. So we have y cubed is equal to 1 plus c e to the minus 3x. Okay, and I suggest to just leave it like that because it looks better. Okay, let's move on to question 4. So question 4 says, what constant interest rate is required if an initial deposit is placed into an account that accrues interest compounding continuously is to double in value in 6 years? So what we have here is y dash as a function of t is some constant, say r, the interest rate, times y. Okay, and so what else do we know? We know that y of 6 is 2 y of 0 because it takes 6 years to double. And so we've got to work out what r is. Okay, now having a look at this differential equation here is both separable and linear. So let's solve this in 2 ways. So this is dy on dt is our y dash, and so we can divide both sides by y, take our dt over, and express this as the integral of dy over y is equal to the integral of r dt, and so that's rt plus some constant c. On the left-hand side, we have the natural log of y. Now, if you want to write that ln, that's totally fine. Okay, and so solving this equation for y, we've got y equals e to the power of rt plus c, but usually we say e to the power of c is just another letter, say a, and so a e to the rt. Okay, now let's use this. So y of 6 is equal to a e to the power of 6r, and that's equal to 2 y of 0, which is 2 a e to the power of 0 times r. And so this is just 2a because e to the power of 0 is 1. Okay, so this equals this. Let's divide both sides by a, assuming that a is non-zero. And so what we get is e to the power of 6 times r is equal to 2. Okay, fine. So now let's solve this equation for r. So what we have then is that 6r is equal to the natural log of 2, but you could write this ln. Okay, and so we just want to divide throughout by 6, and so we have r is equal to 1/6 natural log of 2, and this is approximately 0.1155, or we could say this is 11.5%, compounding continuously. Okay, let's move on to question 5. So a yeast grows at a rate proportional to its present size. So we can express this as y dash is equal to k times y, where y is the present size. If the original amount doubles in 2 hours, okay, so let's write this. Y of 2 is equal to 2 times y of 0. So the question here is, in how many hours will it take to triple? So what we've got to do is solve, not a y, solve y of t is equal to 3y of 0. So we've got to solve this equation for t. Okay, so let's solve this first. So this is dy on dt. Now this equation is separable and it's also linear. So let's solve this as a separable equation. That's probably the easiest way to go. So we've got dy on y integrated is equal to the integral of k dt, which is just kt plus c. On the left-hand side, we have the natural log of y. And so we can solve this for y. So y is equal to a e to the power of kt, where a is e to the power of c. Okay, now we know that y of 2 is 2 times y of 0. So notice y of 0 is equal to a e to the power of 0, which is just a. Okay, and so what this says then, y of 2 is a e to the power of 2k, and this is y of 0, which is a. So a is equal to a e to the 2k. So this gives us a way to find k. Okay, dividing both sides by a, we have e to the 2k is equal to 1. No, not quite, because we missed a 2 in here, didn't we? Yeah, we missed a 2. So 2y of 0, so 2a. So dividing throughout by a gives us 2. Okay, e to the 2k is equal to 2, so 2k is natural log of 2, and so k is equal to 1/2 the natural log of 2. And so we can approximate this, but let's just use our next tool. We're solving for t. Remember, solve y of t is equal to 3y of 0, or 3 times a. Okay, and so y of t is a e to the kt equals 3a. Solving this equation for t, let's cancel the a's on both sides, assuming that's non-zero. And so then we have e to the kt is 3, or kt is the natural log of 3. So this gives us t is equal to 1 over k natural log of 3. But k is 1/2 natural log of 2. So we have 2 log of 3 over log of 2. Where these are the natural logs. Okay, and that's how long it should take. And so as we approximate this, we'll get about 3.17 hours. Okay, let's move on to question 6. A depositor places $10,000 in a certificate of deposit which pays 6% per annum, compounded continuously. How much will be in the account at the end of 7 years, assuming no additional deposits or withdrawals? So what we have here is y of t is 10,000 e to the power of 0.06 t. Right, having solved that equation, now this is y of 0, that's the initial deposit. And so then we can see, we want to know how much will be there at the end of 7 years. So y of 7 is 10,000 e to the power of 7 times 0.06, and that's approximately $15,219.62. Okay, so that one was pretty easy, but let's take some notes here. So note, e to the power of x is the limit as n goes to infinite of 1 plus x over n all to the power of n. And so y of 1 will be 1 plus 0.06 times y to the power of 0 okay, and then y of 2 will be 1 plus 0.06 times y of 1, which is 1.06 squared times y of 0, and so on. Okay, and so this is if it's 6% compounding annually. Now, if we're compounding monthly, what this looks like is y of, after 1 year, is equal to 1 plus 0.06 over 12 all to the power of 12. So you divide that interest rate of 6% by 12, add this to 1, and take that to the 12th power, and that's what you have. Okay, so you can also do this weekly by instead dividing by 52 and taking that to the 52nd power. All right, just some notes there. All right, let's move on to question 7. Determine the interest rate required to double an investment in 8 years under continuous compounding. So we know how this looks. Y of t is equal to a e to the rt. And so what we have then is y of 8 is equal to twice y of 0. And y of 0 is just a. So this is 2a. Okay, we're asked to find the interest rate. So then y of 8 is a e to the 8r, doing this in years, is twice y of 0, so that's 2a. Okay, assuming a is non-zero, dividing by a, we have e to the 8r is 2, and so 8r is the natural log of 2, which you can write as ln of 2 if you like. So dividing both sides by 8, the required interest rate is 1/8 of the natural log of 2, and so that is about 8.66%, or 0.08664, which you can call 8.66%. So in other words, you need an interest rate of 8.66% to double that in 8 years. Okay, I need some more paper, so I'll just grab some. And we'll move on to question 8. Okay, a body of unknown temperature is placed in a refrigerator at a constant temperature of 0 Fahrenheit. After 20 minutes, the temperature of the body is 40 Fahrenheit. After 40 minutes, the temperature of the body is 20 Fahrenheit. Find the initial temperature of the body. Okay, so we have Newton's law of cooling. Which is to say that the rate of the change of the temperature uppercase T with respect to lowercase t is minus K T minus the ambient temperature, but here the ambient temperature is 0. So Tm, or T ambient temperature, is 0 degrees F. Okay, and so we need to solve this, but let's also write the rest of the boundary values. We also know that T of 20 is 40 degrees F. And then let's see, which one are we on? Question 8. After 40 minutes, the temperature is 20, so T of 40 is 20 degrees F. And so we have to find T of 0, the initial temperature of the body. Okay, so solving this equation, it's both separable and linear. So we have dt over t integrated is minus K integral dt. Okay, so we have minus K T plus some C. The left-hand side is the natural log of uppercase T. So log of uppercase T is equal to e to the power of minus kt plus c, but let's express this as a e to the minus kt. Oh, right. Whoops. No e there, so I'm jumping ahead of ourselves. Okay, so we just have this, and now we solve this for uppercase t, and we have t as a function of t is equal to e to the power of this, which we will call a e to the minus kt. Okay, now using our boundary values, t of 20 is equal to a e to the minus 20k, and that's equal to 40. Okay, and so that gives us that gives us this equation. Okay, we can solve that, but the second condition we have is t of 40, which is a e to the minus 40k, is equal to 20. So we have both of these equations. Now dividing the first one by the second one will give us a way to cancel that a. So dividing, we then have e to the power of minus 20k over e to the power of minus 40k is equal to 40 divided by 20, which is 2. Okay, now simplifying the left-hand side, we have e to the power of 40k minus 20k, which is e to the power of 20k, is equal to 2. So this gives us a way to solve for k. So k is equal to the natural log of 2 divided by 20. So we'll write that as 1 over 20 natural log of 2. So this is our k value. All right, now t of 0 is equal to a e to the 0, which is just a. And now we can go back to using one of our equations, such as this one. What we find then is that a is equal to 40 e to the 20k, and so this is 40 times e to the 20 times the natural log of 2 divided by 20. So that's our k there, log 2 over 20. Log 2 over 20, cancel the 20s, and we have e to the power of the natural log of 2, which is 2. So this is 40 times 2, which is 80. And so this 80 that we got is A, which is the initial temperature that we are after. So the answer to this question is 80 degrees Fahrenheit. Okay, let's move on to question 9. A tank initially holds 10 gallons of fresh water. At t equals 0, a brine solution containing 1/2 pound salt per gallon is poured into the tank at a rate of 2 gallons per minute, while the well-stirred mixture leaves the tank at the same rate. Find the amount and concentration of the salt in the tank at time t. Okay, well, we're given in the Schuam outline series, which is where these problems come from, an equation dq on dt is equal to f over v subscript 0 plus e minus f times t all times q is equal to b times e. Here we've got a is equal to 0, b is equal to 1/2, e is equal to 2, f is equal to 2, and v0 is equal to 10. Okay, and so then this gives us dq on dt plus 1/5 of q is equal to 1. Okay, and now this equation is linear. And that should be a plus up here, shouldn't it? Yeah, I believe that should be a plus, because if we sub in the 2, the 10, 2 minus f is 0. So that should just be 2 over 10 is 1/5. So yeah, that's a plus. And then the b times e, 1/2 times 2 is 1. Okay, so that's how we get this linear equation. And so our integrating factor I of t is e to the integral of 1/5 dt, which is e to the power of 1/5 t. Okay, and so this is what we multiply throughout by, but we know how the left-hand side packs up. E to the power of 1/5 t times q, e to the 1/5 t. Now, integrating both sides, we've got e to the 1/5 t times q is the integral of e to the 1/5 t with respect to t. This integral is easy. We just have 5 e to the 1/5 t and then plus c. Now notice that if you differentiate this, you have to bring down a 1/5, which would cancel with the 5 and give you e to the 1/5 t. So this integral is okay. All right, now dividing both sides by e to the 1/5 t, we have q as a function of t is 5 plus c e to the minus 1/5 t. Okay, now we are given in the question that q of 0 is 0. And so that tells you then, subbing 0 in here, that c must be equal to minus 5. E to the 0 is 1. So in other words, what we're solving is 5 plus c equals 0. And so we get c is minus 5. Okay, so now subbing that in there, we've got q of t is equal to 5 minus 5 e to the minus 1/5 t. And so this is the quantity of salt at any given time. Now for the concentration, we have q of t over v subscript 0 plus e minus f of t. This is equal to 5 minus 5 e to the minus 1/5 t all over 10. And so this is our concentration, and we can write this as 1/2 outside of 1 minus e to the minus 1/5 t. Okay, moving on to question 10, and I need to scroll this up so you can see the question. An RC circuit has an EMF of 5 volts, a resistance of 10 ohms, and a capacitance of 10 to the minus 2 farads. So that should be uppercase F for farads. And an initial charge of 5 coulombs on the capacitor. Find the transient current in steady state solution. So we have dq on dt plus 1 over r times c times q is equal to e over r, with r is equal to 10, c is equal to 10 to the minus 2, and e is equal to 5 volts. Okay, so let's sub in these values into our differential equation. So E divided by R is 5 over 10, which is 1/2. So we have dq on dt plus, now RC is the product of these, that's 50. So 1 over 50 R times C is 10 to the minus 1, right? So this is 1 over 1/10, which is 10 Q. And so we said that E divided by R is 1/2. Okay, so there's our differential equation. So the integrating factor, I of t, because this is linear, we have e to the integral of 10 with respect to t. So e to the 10t. All right, now we know how the left-hand side packs up once we multiply by e to the 10t. We have the derivative with respect to t of e to the 10t times q is 1/2 e to the 10t And so now, integrating both sides, e to the 10t times q is the integral of 1/2 e to the 10t dt. And this is 1/20 because we need to divide by the 10 up there in the exponent. So 1/20 e to the power of 10t and then plus some c, our constant of integration. Okay, now dividing both sides by e to the 10t, we have q as a function of t is equal to 1/20 plus c e to the minus 10t. Okay, next, q of 0 is 5. And so we have 5 is equal to 1/20 plus c e to the 0. So 1/20 plus c. And so that gives us that c is equal to 5 minus 1/20. So placing this over 20, we have 5 times 20 is 100 minus 1 all over 20, which is 99/20. Okay, and so we have q of t is 1/20 outside of 1 plus 99 e to the minus 10t. The transient current, which is what we're asked for, find the transient current and the steady state current. So the transient current is lowercase I of t, which is dq on dt. And so we need to differentiate this with respect to t. So that brings down a minus t. The derivative of 1/20 is 0. And then this derivative, the derivative of 99 e to the minus 10t is minus. The derivative of 99 e to the minus 10t over 20 is minus 99/20 times 10 e to the minus 10t. Okay, in other words, minus 99/2 e to the minus 10t. And then the steady state current is just the limit as t goes to infinite of I of t, which will be 0 in this case. Okay. Moving on to the last question. So this one says solve y dash equals minus 2y plus e to the power of t y cubed, where y of 0 is 1. Okay, now this one is Bernoulli because we can write this as y dash plus 2y is e to the power of t y cubed, where here n is equal to 3. So what we do is we let z be equal to y to the power 1 minus n, which is y to the power 1 minus 3, or y to the minus 2. Now we differentiate this with respect to t, because we have a t here. So z dash of t is equal to minus 2y to the power of minus 3 times y dash of t. And so this then tells us that y dash, solving this for y dash, is equal to minus a half y cubed z dash. Okay, and now we can sub this in where we see y dash. So we have minus 1/2 y cubed z dash plus 2y equals e to the t y cubed. Okay, we want to divide this throughout by this term. And so then when we do, we've got z dash, okay, 2 divided by minus 1/2 is minus 4. So y over y cubed is y to the power of minus 2, which is z. So minus 4z equals minus 2e to the t. Y cubed divided by y cubed is 1. All right, great. So now this equation is linear. And so we can solve it using an integrating factor. So I of t is our integrating factor, e to the power of the integral of minus 4 dt. So we've got e to the minus 4t. Okay, multiplying this on left and right hand sides, the left hand side packs up as the derivative with respect to t of e to the minus 4t multiplied by z, and then on the right hand side we take the sum of those exponents, so we have minus 2 e to the minus 3t. And so we need to integrate both sides, and we get e to the minus 4t times z is equal to the integral of minus 2 e to the minus 3t with respect to t. Okay, this integral is easy. We just have 2/3 e to the minus 3t then plus c. And so now we just need to solve this for z and recognize that z is y to the minus 2. So y to the minus 2 is equal to 2/3 e to the power of 4t minus 3t is 1t plus c e to the 4t. And so what we get is, inverting both sides, y squared is equal to 1 over 2/3 e to the t plus c e to the 4t. All right, fantastic. That completes the problem set. Thanks.